Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the deep time story of mountains that rise and fall like slow breaths across Earth's sleeping face. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. There stands a mountain that exists only in the imagination now, its summit dissolved into the memory of stone. Once, perhaps 200 million years ago, this peak stretched toward a sky that knew different constellations, its granite face catching light from a sun that shone on creatures Earth has long forgotten. The mountain rises in the mind's eye, majestic and seemingly permanent, its ridgelines sharp against ancient clouds that carried the moisture of vanished seas. Snow capped its highest reaches in winters that lasted centuries, while its lower slopes knew the footsteps of reptiles whose names exist only in Latin now, creatures that crawled through fern forests where pine trees would not grow for another 100 million years. Even as this vision forms in the quiet spaces of contemplation, the mountain begins its patient journey toward becoming something else entirely. Sand grains scattered across distant shores that have not yet emerged from ocean floors. Clay particles settling in basins where future rivers will carve their meandering signatures through rock layers yet to be compressed into stone. Minerals dissolved in groundwater that seeps through limestone caverns still forming in the warm, shallow seas of continents that drift like sleeping giants across the planet's restless surface. The mountain that was never there teaches a quiet lesson about impermanence, written in the language of crystal lattices and chemical bonds. Every peak that pierces today's horizon carries within its crystalline structure the seeds of its own disappearance, encoded in the very minerals that give it strength. Granite, which seems so solid beneath hiking boots and so eternal beneath the weight of centuries, contains feldspar crystals that yearn to become clay when touched by slightly acidic rainwater. These crystals, born in the deep furnaces of magma chambers miles beneath the Earth's surface, emerge into a world of water and oxygen that slowly teaches them to forget their volcanic origins. The very act of standing tall exposes stone to weathering processes that work with the patience of geological time. Temperature changes expand and contract rock faces in rhythms measured not in seasons but in millennia. Frost wedging works its slow magic in cracks so small they would be invisible to human eyes, yet large enough to admit water that freezes and expands with the quiet force that can split continents. Root systems find their way into hairline fractures, growing with the persistence of life-seeking light, their expansion adding pressure that accumulates across centuries like interest in some cosmic bank account. Scientists study mountains that vanished before the first trees grew, reading their stories in the sedimentary layers they left behind like pressed flowers in an ancient book. These phantom peaks live on in the sandstones and shales that record their dissolution, their mineral signatures preserved in rock formations that speak of highlands that once caught rain clouds and redirected the flow of ancient rivers. The Taconic Mountains of eastern North America tell such a story. Their former heights now scattered across the continent in layers of sediment that preserve the memory of peaks that rivaled the modern Appalachians in their youth. In the Australian outback, the Pilbara region reveals the ghosts of mountain ranges that rose and fell during the Archean Eon, when Earth's atmosphere contained no free oxygen and the sun shone with 70% of its current brightness. These vanished mountains left behind banded iron formations that paint the landscape in rusty stripes, each band representing thousands of years of chemical precipitation in ancient seas. The iron came from the weathering of volcanic peaks that no longer exist, their substance redistributed across ocean floors that have since been uplifted, folded, and exposed to the light of a sun that has grown steadily brighter across the eons. What mystery hides in this vanishing that seems so complete, so thorough, that entire mountain ranges can disappear without leaving behind even their roots? How does something so substantial, so seemingly eternal, simply fade away grain by grain until not even its foundations remain to mark where giants once stood? The answer lies not in catastrophe, but in the gentle, relentless arithmetic of erosion, a process so slow that 10 million human lifetimes would barely register its progress, yet so thorough that it can level mountain ranges taller than the Himalayas and scatter their substance across ocean basins thousands of miles away. The mathematics of disappearance work on scales that dwarf human comprehension. A mountain range losing 1 millimeter of height per year, barely the thickness of a fingernail, will surrender 1,000 meters of elevation in 1,000,000 years. A time span that represents the entirety of human evolution compressed into a single geological moment. At such rates, peaks that tower 6 kilometers above sea level will be reduced to rolling hills in 6 million years, and to flat plains in 12 million years, assuming no other forces intervene to complicate the arithmetic. Yet even as mountains dissolve, the very process of their dissolution creates the conditions for new mountains to rise elsewhere. The sediments carried away by rivers accumulate in vast basins where they will eventually be compressed into sedimentary rocks. These rocks, in turn, may be caught in future tectonic collisions and folded upward into new mountain ranges, their layers telling the story of the ancient peaks from which they came. The limestone cliffs of the Canadian Rockies contain fossils of marine creatures that lived in shallow seas fed by the erosion of mountains that vanished long before the Rockies themselves began to rise. Only took 1 billion years for the first mountains to learn how to disappear into the patient embrace of wind and weather. Only took another 1 billion years for Earth to perfect the art of making them reappear somewhere else, recycled through the slow breathing of tectonic plates. Only took geology this long to discover that permanence is the greatest illusion of all, that even the most enduring features of the landscape are merely temporary arrangements of atoms waiting for their turn to dance in different configurations. In the deep places where continents dream, tectonic plates drift toward their inevitable meeting with the slowness of fingernails growing in the darkness. Two vast slabs of lithosphere, each carrying the weight of entire continents upon their backs, approach each other across an ocean that has been shrinking for 50 million years. The distance between them closes at the rate of centimeters per year, a pace so measured that entire species evolve and vanish in the time it takes for the gap to narrow by the width of a mountain range. Yet this glacial convergence carries within it the compressed energy of a planet in motion, forces sufficient to fold solid rock like clay in the hands of some cosmic sculptor working on timescales that reduce human history to the briefest flicker. The ocean floor between these approaching giants tells the story of their courtship in magnetic stripes that record the reversals of Earth's magnetic field across geological ages. These zebra-like patterns in the basalt preserve the memory of mid-ocean ridges where new seafloor once spread outward like a slow-motion explosion, creating crust that now travels toward its destiny in the crushing embrace of continental collision. Seamounts that once rose from abyssal plains now find themselves caught between the advancing plates, their volcanic peaks destined to become the exotic terrains that will add their foreign signatures to the heart of a future mountain range. The collision begins not with the dramatic crash that human imagination might envision, but with a gentle touching that occurs first in the deepest places, where the leading edges of the continental margins meet beneath miles of sedimentary layers. Here, in the darkness far below the reach of sunlight, the first compressions begin to fold the accumulated debris of ancient ocean floors into the early structures that will one day pierce the sky. Limestone beds that recorded the quiet lives of countless marine creatures start their slow journey upward, carrying with them the compressed history of seas that will soon exist only in the fossil record. Ocean sediments, soft as butter in geological terms, respond to the mounting pressure by flowing like viscous liquid, their layers folding into complex geometries that will puzzle geologists millions of years in the future. Sandstones that once lay horizontal on ocean floors begin to tilt toward the vertical, their ancient ripple marks and cross-bedding now standing on edge like the pages of an enormous book being slowly closed by invisible hands. Shales that accumulated grain by grain in the quiet depths transform under pressure and heat, their clay minerals recrystallizing into slate and schist that will one day gleam in mountain streams not yet carved. The mathematics of continental collision operate according to principles that seem to violate common sense. When an unstoppable force meets an immovable object in the realm of plate tectonics, both give way through a process called plastic deformation. The continental crust, despite being composed of solid rock, behaves like thick honey when subjected to the patient pressure of geological time. It flows upward and outward, seeking release from the mounting stress, creating the broad upwarps and downwarps that will define the future geography of the collision zone. Deep beneath the developing mountain range, temperature and pressure reach values that transform the very nature of rock itself. Granite begins to partially melt, creating pockets of magma that will rise through the overlying crust like bubbles in a lava lamp, their ascent measured in thousands of years rather than seconds. These plutonic intrusions will cool slowly in their underground chambers, forming the massive batholiths that will serve as the structural backbone of the mountain range, their coarse-grained texture recording the leisurely pace of their crystallization in the Earth's deep places. The surface remains deceptively calm during these early stages of mountain building, betraying little sign of the titanic forces at work below. Shallow seas still cover much of the collision zone, their waters warm and clear, supporting coral reefs and marine communities that have no knowledge of the transformation taking place beneath their calcium carbonate foundations. Occasionally, earthquakes ripple through the region, their tremors barely noticeable compared to the violent shaking that will characterize later stages of the collision. These gentle warnings hint at the adjustments occurring in the deep architecture of the crust, the slow settling and shifting of rock masses that are learning to accommodate their new configuration. What mystery lies in the fact that such overwhelming forces can work so quietly, so gradually, that their effects remain hidden for millions of years? The energy released in mountain-building episodes exceeds that of countless atomic explosions, yet this energy dissipates so slowly, so evenly, that life continues largely undisturbed on the surface. The secret lies in the vast timescales over which these forces operate, distributing their intensity across eons so that each individual moment carries only a whisper of the total transformation. Scientists studying modern collisional zones observe this process in its various stages, from the initial touching of continental margins in places like the Mediterranean, where Africa nudges against Europe with imperceptible persistence, to the full-scale mountain building occurring in the Himalayas, where India continues its 50-million-year journey into the heart of Asia. Each collision zone offers clues to the others, creating a library of mountain-building processes that spans the globe and reveals the common patterns underlying these monumental transformations. Only took 50 million years for continents to close an ocean and begin the delicate work of folding stone into sky-reaching architecture. only took geology this long to realize that the most violent forces in nature often work through patience rather than drama. Only took mountains this long to discover that their birth requires the death of oceans, their rise demanding the sacrifice of the deep places where life first learned to build shells from dissolved limestone. The arithmetic of uplift begins its calculations in increments so small they mock human perception of progress, yet so relentless that they accumulate into monuments that dwarf the works of civilization. Millimeter by millimeter, the compressed sediments and folded rocks respond to the deep pressures generated by continental collision, their molecular structures adjusting to forces that build like interest, compounding in some geological bank account. A single millimeter of elevation gained per year. Barely the thickness of a credit card will raise a mountain range 1,000 meters in a million years, a time span that encompasses the entire evolutionary history of grass, yet represents merely a moment's hesitation in the grand narrative of planetary transformation. Beneath the emerging highlands, the principle of isostatic equilibrium governs the rise of continents with the same mathematical precision that controls ships floating in harbor. As sedimentary layers thicken and volcanic rocks accumulate, their increasing mass depresses the underlying mantle, which responds by flowing laterally away from the zone of compression like honey displaced by a heavy spoon. This downward flexing creates space for more material to accumulate, establishing a feedback loop that can continue for tens of millions of years, each cycle adding height to the developing mountain range while simultaneously deepening its roots into the plastic layers of the upper mantle. The crust thickens beneath the rising peaks like skin forming over a healing wound, its normal thickness of 35 kilometers doubling and sometimes tripling as rock layers stack upon one another in impossible geological configurations. Limestone formations that originated in tropical seas find themselves sandwiched between granite plutons and metamorphic schists. Their fossil corals and marine shells now embedded in rock masses that tower 6,000 meters above the nearest ocean. These vertical displacements represent one of geology's most profound paradoxes, the fact that the highest places on Earth preserve the most complete records of ancient ocean floors, their summit rocks having traveled further from sea level than any other stones on the planet's surface. Gravity pulls downward with unchanging persistence throughout this process, its force constant and reliable as sunrise, yet somehow unable to prevent the continued ascent of rock masses that seem to defy its fundamental authority. The secret lies in the greater forces generated by plate convergence, which overwhelm gravity's conservative influence through the application of horizontal pressures that exceed the vertical pull by orders of magnitude. When continents collide, they generate stress fields that can lift entire crustal blocks despite the downward pull of their own increasing mass, creating a situation where mountains literally pull themselves up by their own geological bootstraps. The deep structure of rising mountain ranges reveals architectural principles that would challenge any human engineer attempting to design stable structures at such scales. Thrust faults slice through the crust at low angles, allowing older rocks to override younger formations in violations of normal stratigraphic relationships that puzzle geologists for decades after their discovery. These fault systems can transport rock masses hundreds of kilometers from their points of origin, stacking different geological terrains like a shuffled deck of cards whose original order becomes impossible to determine without sophisticated analysis of their mineral compositions and fossil contents. Metamorphic processes accompany the uplift, transforming sedimentary rocks into new crystalline structures through the application of heat and pressure that operate like slow-motion alchemy in the Earth's deep laboratories. Shale becomes slate, then schist, then gneiss as temperatures and pressures increase with depth and time, each transformation marking a step in the rock's journey toward complete recrystallization. Limestone converts to marble, its original fossil textures obliterated by the growth of new calcite crystals that form interlocking mosaics of mineral grains arranged in patterns that reflect the stress fields operating during their formation. Temperature gradients within the thickening crust create zones of partial melting, where granite magmas form through the breakdown of existing rock minerals, their chemistry reflecting the complex history of their source materials. These magmatic intrusions rise through the overlying rocks like enormous underground rivers of molten stone, their ascent driven by their lower density compared to the surrounding solid formations. As they cool and crystallize in underground chambers, they form plutonic bodies that will eventually be exposed by erosion, their coarse-grained textures recording the slow pace of their cooling in the insulated environment of the deep crust. What mystery governs the balance between uplift and the immediate response of erosional processes that begin their work the moment rock surfaces emerge above sea level? The first rainfall on newly exposed bedrock initiates chemical weathering reactions that will continue for millions of years. Yet the rate of uplift often exceeds the rate of erosion during the active phases of mountain building, allowing peaks to grow higher despite the constant assault of wind, water, and temperature changes. This race between construction and destruction creates the dynamic equilibrium that determines the ultimate height of mountain ranges, with factors such as climate, rock type, and tectonic convergence rate all contributing to the final outcome. Modern GPS measurements reveal that some peaks in active mountain ranges continue to rise at rates of several centimeters per year, their elevation increasing fast enough to be detected by satellite monitoring systems that can measure vertical displacements with millimeter precision. The Himalayan peaks grow taller each year as the Indian subcontinent continues its collision with Asia, though their ultimate height remains limited by the increasing efficiency of erosional processes at extreme elevations, where freeze-thaw cycles and high winds accelerate the breakdown of exposed rock surfaces. Only took mountains this long to discover that rising requires more than simple buoyancy, that the arithmetic of elevation demands a complex balancing act between the forces that build and those that destroy. Only took geology this long to realize that the highest places on Earth are also the most temporary, their very height making them vulnerable to the atmospheric processes that will eventually return them to sea level. Only took 30 million years for the Himalayas to learn that every meter gained through uplift must be defended against the patient work of monsoon rains and glacial ice. When stone learns to breathe, it does so through the molecular choreography of chemical weathering, a process that begins the moment crystalline minerals encounter the alien chemistry of Earth's surface environment. Feldspar crystals, born in the sterile heat of magma chambers where oxygen exists only in chemical bonds, emerge into a world of free atmospheric gases and slightly acidic rainwater that teaches them the art of dissolution. The first droplets of moisture that touch newly exposed granite initiate reactions that will continue for millions of years, each water molecule carrying the potential to liberate ions from their crystalline prisons and send them wandering toward distant ocean basins. The atmosphere itself becomes an active participant in the mountain's transformation. Its mixture of nitrogen, oxygen, and trace amounts of carbon dioxide creating conditions that ancient rocks have never experienced. Carbon dioxide dissolves in rainwater to form carbonic acid, a weak solution no stronger than carbonated beverages, yet persistent enough to slowly disassemble the mineral frameworks that give granite its apparent permanence. This atmospheric chemistry operates like a planetary respiratory system, with each rainfall representing an exhalation of chemical potential that gradually converts solid rock into dissolved ions and clay particles suspended in the thin films of water that coat every exposed surface. Potassium feldspar, one of the most abundant minerals in continental crust, undergoes hydrolysis reactions that proceed with the measured pace of geological time. Water molecules insert themselves into the crystal lattice structure, disrupting the orderly arrangement of silicon, aluminum, and potassium atoms that define the mineral's identity since its formation in underground magma chambers millions of years earlier. The freed potassium ions migrate away in groundwater solution, while the remaining silicon and aluminum atoms reorganize themselves into clay minerals that retain the memory of their feldspar ancestry in their layered crystal structures. Temperature fluctuations accelerate these chemical processes through principles borrowed from basic chemistry, where reaction rates approximately double for every 10 degrees Celsius of warming. The daily and seasonal temperature cycles that characterize mountain environments create alternating periods of enhanced and reduced chemical activity, with warm afternoons driving rapid weathering reactions, while cold nights slow the molecular motion that enables ion exchange. Over geological timescales, these temperature variations integrate into powerful agents of rock decomposition. Their cumulative effects, measured not in days or seasons, but in the millions of years required to convert entire mountain faces into mobile sediment. Organic acids produced by the first pioneer organisms to colonize newly exposed rock surfaces add their own chemical signatures to the weathering process. Lichens, among the most resilient life forms on Earth, secret organic compounds that can dissolve minerals more efficiently than simple carbonic acid. Their biochemical warfare conducted at the scale of individual crystals. These biological agents represent evolution's contribution to the mountain's dissolution, life itself becoming an ally of the erosional processes that will eventually level the peaks and scatter their substance across lower elevations. The pH of natural rainfall varies between regions and climates, but even the purest precipitation maintains a slightly acidic character due to its equilibrium with atmospheric carbon dioxide. This universal acidity means that every mountain range on Earth experiences chemical weathering from the moment of its emergence above sea level, regardless of local climate conditions. In tropical regions, where high temperatures and abundant rainfall combine to maximize chemical reaction rates, weathering proceeds with particular intensity, creating thick soils and deep zones of altered rock that can extend hundreds of meters below the surface. Plagioclase feldspar, calcium-rich cousin to the potassium variety, responds to chemical weathering by releasing calcium ions that will eventually find their way to ocean basins where they contribute to the formation of limestone through biological and chemical precipitation processes. This calcium represents a direct chemical link between mountain uplift and marine sedimentation, each dissolved ion carrying information about the mineral composition and weathering history of its highland source. The calcium content of ancient limestones thus preserves indirect records of mountain ranges that vanished millions of years before the sedimentary rocks formed. Biotite mica, with its dark sheets of iron and magnesium-bearing minerals, weathers along different pathways that release these metallic elements into groundwater systems where they participate in complex geochemical cycles. Iron oxidizes in the presence of atmospheric oxygen, creating the rusty stains that color weathered granite surfaces and give many soils their characteristic reddish hues. This iron oxidation represents one of the most visible signs of chemical weathering, painting the landscape in earth tones that reflect the ongoing transformation of primary minerals into secondary weathering products. What mystery lies in the fact that the strongest rocks prove most vulnerable to the weakest acids? That granite capable of supporting mountain ranges crumbles before solutions barely more corrosive than rainwater? The answer resides in the thermodynamic instability of high-temperature minerals when exposed to low-temperature surface conditions. Feldspar crystals exist in a state of chemical disequilibrium with their surface environment, their internal energy levels reflecting the extreme conditions of their formation rather than the moderate temperatures and pressures that characterize the Earth's surface. Quartz stands apart from its fellow granite minerals in its resistance to chemical weathering. Its simple silicon dioxide structure proving remarkably stable under surface conditions. While feldspar and mica surrender their constituent elements to passing waters, quartz crystals maintain their crystalline integrity, accumulating as resistant grains in soils and sediments. This differential weathering creates the textural changes that gradually transform granite from a coherent rock mass into a disaggregated collection of quartz grains and clay particles, each component following its own pathway through the chemical cycles that connect mountain erosion to ocean sedimentation. Only took millions of years for feldspar to learn that atmospheric chemistry operates by different rules than magmatic chemistry, that surface conditions favor clay minerals over the crystalline structures that dominated the deep earth. Only took granite this long to discover that its apparent strength masks a fundamental vulnerability to the patient work of slightly acidic water. Only took chemical weathering this long to demonstrate that the most powerful geological forces often work through the gentlest means, dissolving mountains one molecule at a time. The first fracture arrives as an invitation written in the language of thermal expansion, a hairline crack so narrow that morning dew barely penetrates its depths, yet wide enough to admit the molecular agents that will spend the next million years widening it into a canyon. This initial breach in the granite's crystalline armor appears during a particularly cold autumn night, when temperatures drop below freezing for the first time since the mountain's emergence above the permanent snow line. Water trapped in microscopic pores within the rock expands as it crystallizes into ice, exerting pressures that exceed the tensile strength of stone, with the quiet persistence of winter settling into the high places. The physics of frost wedging operate according to principles that seem almost gentle in their simplicity, yet prove devastating in their cumulative effects across geological time. Water expands by approximately 9% when it transforms from liquid to solid, creating volumetric forces that can generate pressures exceeding 2,000 pounds per square inch within confined spaces. This expansion occurs slowly, over hours rather than seconds, allowing ice crystals to grow with deliberate precision into every available void, their formation pushing against rock walls with the inexorable force of crystallization itself, seeking space to express its geometric perfection. Each freeze-thaw cycle widens existing cracks by microscopic amounts, the repeated expansion and contraction working like a geological ratchet that allows incremental progress but prevents retreat. During the warming phases of daily temperature cycles, meltwater penetrates deeper into the expanding network of fractures, carrying dissolved minerals and clay particles that prevent the cracks from healing when temperatures drop again. This process creates a feedback mechanism where successful fracturing enables deeper water penetration, which in turn enables more extensive fracturing during subsequent freeze cycles. The mountain's elevation determines the frequency and intensity of these freeze-thaw events, with peaks above the tree line experiencing hundreds of such cycles each year, while lower elevations undergo only occasional episodes of frost action. Alpine environments exist in a perpetual state of thermal warfare between day and night, summer and winter. Their exposed rock faces subject to temperature swings that can exceed 50 degrees Celsius within a single 24-hour period. These extreme variations create stress fields within the rock that propagate outward from temperature boundaries, generating networks of incipient fractures that await the arrival of water to complete their transformation into active erosional pathways. Crystalline rocks prove particularly susceptible to frost wedging due to their heterogeneous mineral compositions, which respond differently to temperature changes and create internal stress concentrations at grain boundaries. The interface between quartz and feldspar crystals becomes a preferred location for crack initiation, as these minerals possess different coefficients of thermal expansion that cause them to grow and shrink at slightly different rates during temperature fluctuations, over thousands of heating and cooling cycles. These differential movements gradually weaken the bonds between adjacent mineral grains, creating microscopic separations that provide entry points for water and the subsequent ice formation that will widen them into visible fractures. Joint systems develop through the intersection of multiple fracture networks, creating geometric patterns that reflect the stress history of the rock mass and the orientation of maximum thermal gradients. These joints often follow predictable orientations related to the cooling history of plutonic rocks or the foliation planes inherited from metamorphic processes. But frost wedging modifies and extends these existing weaknesses into complex three-dimensional networks that can extend hundreds of meters into the mountain's interior. The resulting fracture patterns create the architectural blueprint for future mass-wasting events, defining the pathways along which large rock masses will eventually separate from the parent bedrock. Sheet joints form parallel to exposed rock surfaces through a different mechanism that involves the relief of confining pressure as overlying rock masses erode away. These fractures create curved surfaces that follow the topographic contours of the mountain, peeling away like layers of an onion to expose fresh rock surfaces to renewed cycles of thermal stress and frost action. The combination of sheet jointing and frost wedging creates a systematic method for exposing ever deeper levels of the mountain's interior to surface weathering processes, ensuring that the destructive effects of temperature cycling penetrate far beyond the immediate surface layers. The seasonal rhythm of fracture propagation follows the mountain's climatic calendar, with maximum activity occurring during the spring and fall months when frequent transitions between freezing and thawing temperatures create optimal conditions for ice crystal growth. Winter temperatures that remain consistently below freezing actually slow the fracturing process by maintaining water in its solid state, while summer temperatures that stay above freezing eliminate the expansion forces entirely. The peak effectiveness of frost wedging thus occurs during the transitional seasons, when temperature fluctuations cross the critical threshold of 0 degrees Celsius with predictable regularity. What mystery governs the precise angles at which fractures propagate through crystalline rock, following pathways that seem to anticipate the mountain's future collapse into talus slopes and scree fields? The answer lies in the stress field analysis that governs crack propagation in elastic materials, where fractures follow trajectories of maximum tensile stress while avoiding directions of compressive loading. These stress trajectories are determined by the mountain's gravitational loading, its thermal history, and the orientation of existing weak planes inherited from earlier geological processes. Permafrost regions experience modified versions of frost, wedging where permanently frozen ground creates unique conditions for fracture development. In these environments, active layer processes near the surface generate seasonal freeze-thaw cycles, while deeper permafrost provides a stable foundation that can concentrate stress fields in narrow zones of thermal activity. The presence of ground ice in permafrost regions adds another dimension to the fracturing process, as large ice masses can expand and contract in response to long-term climate variations, creating deformation that affects entire mountain slopes over timescales of centuries rather than days. Only took frost this long to learn that patient repetition accomplishes what sudden violence cannot, that the gentlest expansion forces can split mountains when applied consistently across geological time. Only took ice this long to discover that its greatest power lies not in glacial scouring, but in the quiet crystallization that occurs in the hidden spaces between mineral grains. Only took winter this long to demonstrate that destruction often begins with an invitation so subtle that few notice its arrival until the damage has already become irreversible. Rivers write their signatures across the mountain's face with liquid persistence, their flowing waters following gravity's invitation toward the distant sea, while carving stories of elevation and time into the stone substrates that define their channels. Each droplet of precipitation that lands on the mountain's summit begins its journey as part of a vast hydrological manuscript, its path predetermined by the subtle topographic variations that will guide it through an intricate network of rills, streams, and eventually major river systems that drain the highlands' accumulated moisture toward base level. The mathematics of this flow operate according to principles that seem almost literary in their precision, with each tributary contributing its own narrative thread to the larger story of landscape transformation through the patient work of running water. The initial formation of drainage networks follows patterns that reflect both the underlying geological structure and the random variations in surface topography that determine where water first begins to concentrate into coherent flows. Headward erosion allows streams to extend their reach upslope through the systematic lowering of channel beds, a process that works backward from established drainage outlets toward the highest elevations like geological archaeology conducted in reverse. Each storm event contributes to this upslope migration, as increased discharge provides the energy necessary to dislodge and transport sediment particles that have been loosened by the chemical and physical weathering processes operating on exposed bedrock surfaces. Stream power varies as a function of discharge and channel gradient, creating a relationship where steep mountain streams possess enormous erosive potential despite their relatively small volumes of water. The energy available for erosion increases dramatically during flood events, when normal flows expand to fill entire valley bottoms and mobilize sediment loads that can exceed the annual transport capacity by orders of magnitude within the span of a few hours. These episodic high-energy events accomplish most of the long-term erosional work, with decades of quiet flow interrupted by brief periods of intense geological activity that reshape entire drainage basins. Bedrock channels develop through the systematic removal of jointed rock masses along fracture planes that provide pathways of least resistance for flowing water. The hydraulic forces generated by turbulent flow exploit existing weaknesses in the rock structure, gradually widening joints and fault planes into channels that can accommodate increasingly larger volumes of runoff. Plucking occurs when water pressure behind loose rock blocks exceeds their gravitational and adhesional attachment to the channel floor, allowing entire sections of bedrock to be lifted and transported downstream during high-flow events that occur perhaps once or twice per decade. Abrasion contributes additional erosive power through the grinding action of sand and gravel particles suspended in the flowing water. These sediment loads acting like liquid sandpaper that slowly wears away the bedrock surfaces over which they travel. The effectiveness of this abrasional erosion depends on both the hardness of the transported particles and the velocity of their movement, with quartz-rich sediments proving particularly effective at abrading softer minerals such as feldspar and calcite. The resulting erosional patterns often reflect the differential resistance of various rock types, creating channels that preferentially follow zones of weakness while leaving more resistant formations standing as ridges between adjacent valleys. Chemical erosion operates simultaneously with these mechanical processes, as the slightly acidic character of natural stream water enables the dissolution of susceptible minerals along channel margins and beds. Limestone proves particularly vulnerable to this chemical attack, with carbonic acid in stream water converting calcium carbonate into soluble calcium bicarbonate that disappears invisibly into the flow. The resulting solution, channels and limestone pavements, create distinctive erosional landscapes where surface drainage networks become integrated with subsurface cave systems that continue the erosional process below the visible landscape. Nick points develop where streams encounter resistant rock units or structural features that temporarily halt their downward cutting, creating waterfalls and rapids that represent disequilibrium conditions in the longitudinal profile of the drainage system. These features migrate upstream through continued erosion at their base, gradually extending the reach of efficient stream, cutting into previously protected headwater areas. The migration rate of nick points depends on rock resistance and stream power, with some features retreating upstream at rates of meters per year, while others maintain stable positions for thousands of years. Valley widening accompanies the downward cutting process as mass wasting events deliver additional sediment to stream channels from the surrounding hill slopes. These contributions, often triggered by stream undercutting, that steepens valley walls beyond their angle of repose. The resulting valley cross-sections reflect the balance between vertical incision and lateral erosion, with narrow V-shaped profiles characterizing rapidly cutting streams, while broader valleys indicate longer periods of lateral planation and hill slope adjustment. Climate variations influence this balance by controlling both the magnitude of peak discharges and the frequency of mass wasting events that supply sediment to the drainage system. What mystery governs the precise spacing and branching patterns of tributary networks, creating drainage densities that seem to optimize the collection and transport of surface runoff across the mountain's varied topography? The answer lies in the self-organizing properties of erosional systems, where stream channels develop according to principles of energy minimization that automatically adjust network geometry to achieve maximum efficiency in sediment transport. These patterns emerge naturally from the interaction between flowing water and erodible surfaces, creating fractal-like structures that repeat at multiple scales throughout the drainage basin. Capture events occasionally redirect entire river systems when aggressive headward erosion allows one stream to intersect and divert the flow of an adjacent drainage network. These stream piracy episodes, representing dramatic reorganizations of regional hydrology that can occur over timescales of thousands rather than millions of years. The abandoned valley segments created by these capture events become wind gaps that preserve evidence of former drainage patterns, their dry channels telling stories of rivers that once flowed through landscapes now drained by entirely different stream systems. Base level changes, whether caused by tectonic uplift, climate variations, or downstream damming events, propagate upstream through drainage networks as waves of renewed erosional activity that can rejuvenate previously stable channel systems. These perturbations demonstrate the interconnected nature of erosional landscapes, where changes in one part of the system eventually influence erosional processes throughout the entire drainage basin, often with time lags that span thousands of years as the effects of base-level adjustment work their way through the hierarchical network of tributaries and main stem channels. Only took rivers this long to learn that patient flow accomplishes what violent floods cannot sustain, that the most effective erosion occurs through consistent application of moderate forces rather than episodic applications of extreme energy. Only took streams this long to discover that their greatest power lies in persistent downward cutting rather than lateral wandering. That depth leads to capture and eventual dominance over adjacent drainage systems. Only took flowing water this long to demonstrate that liquid persistence can carve canyons through the hardest rocks, writing stories of elevation loss in the permanent language of bedrock channels. The glacier learns to sculpt stone through an apprenticeship that spans tens of thousands of years, its education beginning with the simple accumulation of snow in high cirques where summer melting fails to eliminate winter's patient deposits. Layer upon layer of crystalline precipitation builds into névé fields that gradually transform under their own weight. The delicate hexagonal structures of individual snowflakes collapsing and recrystallizing into granular firn that marks the first stage in ice's metamorphosis from atmospheric moisture into a geological agent capable of reshaping entire mountain ranges. This transformation occurs with the measured pace of deep time, each annual increment adding mass to accumulation zones that will eventually generate the pressure gradients necessary to initiate downslope flow. The physics of glacial motion operate according to principles that seem to contradict the solid nature of ice. This crystalline material behaving like an extremely viscous fluid when subjected to the persistent stress of its own accumulated mass, plastic deformation occurs within ice masses that exceed critical thickness thresholds, typically around 30 meters, where the pressure at the base becomes sufficient to enable crystal boundary sliding and internal shear that allows the entire mass to flow downslope under gravitational influence. This flow proceeds at rates measured in meters per year rather than the centimeters per second that characterize liquid water, yet proves devastating in its cumulative effects across the millennia required for glacial cycles to complete their erosional work. Basal sliding contributes additional velocity to glacial movement when the interface between ice and bedrock reaches pressure melting point, creating thin films of liquid water that serve as lubricating layers between the glacier and its rocky foundation. The pressure-induced melting occurs even at temperatures below the normal freezing point of water, as the enormous weight of overlying ice depresses the melting temperature through thermodynamic principles that enable liquid water to exist under conditions that would normally favor ice formation. This basal lubrication allows glaciers to slide across their beds with velocities that can exceed their internal flow rates, creating complex patterns of glacial motion that vary seasonally with changes in meltwater production and subglacial hydrology. Freeze-thaw processes at the glacier-bedrock interface create conditions for plucking that exceed the effectiveness of any other erosional agent operating in mountain environments. Meltwater penetrates into bedrock fractures, where it refreezes during periods of reduced pressure or temperature, creating ice-filled joints that become incorporated into the moving glacier mass. When the glacier advances, these frozen attachments allow it to literally pull apart the bedrock, removing entire blocks of stone that become incorporated into the glacial debris load as angular clasts that will serve as abrasional tools during subsequent transport. This quarrying process operates most effectively on well-jointed bedrock, where existing fracture systems provide planes of weakness that glacial action can exploit. Subglacial abrasion occurs through the grinding action of rock debris frozen into the glacier's soul, creating conditions where the ice mass acts like a gigantic piece of sandpaper moving across the landscape with inexorable persistence. The embedded rock fragments score and polish the underlying bedrock, creating the distinctive striations and chattermarks that preserve directional records of former ice flow long after the glaciers themselves have retreated. The effectiveness of this abrasional process depends on the hardness differential between the abrading particles and the bedrock surface, with quartz-rich debris proving particularly effective at wearing away softer minerals, such as feldspar and calcite, that compose much of the continental crust. Cirque development represents one of glacial erosion's most distinctive accomplishments, as repeated episodes of ice accumulation and flow gradually excavate amphitheater-shaped basins in mountain headwalls through the combined effects of plucking, abrasion, and frost weathering enhanced by the presence of persistent ice masses. The steep back walls of cirques retreat through freeze-thaw processes that operate with particular intensity, where glacial ice alternately covers and exposes bedrock surfaces to temperature fluctuations. These headward eroding cirques eventually intersect to create knife-edge ridges called arêtes, and where three or more cirques meet, they generate pyramidal peaks called horns that represent the final stages of glacial dissection. U-shaped valley profiles distinguish glacial erosion from the V-shaped channels characteristic of stream erosion, reflecting the different erosional mechanics employed by ice masses that fill entire valley bottoms compared to concentrated water flows that cut narrow channels. Glacial valleys exhibit parabolic cross-sections that result from the plastic flow characteristics of ice, which distributes erosional forces across the full width of the valley floor rather than concentrating them along a narrow central channel. The depth of glacial erosion often exceeds that achieved by streams in similar time periods, as ice masses can maintain erosional contact with bedrock across much larger surface areas than flowing water. Hanging valleys form where tributary glaciers fail to erode as deeply as the main valley glacier, creating step-like discordances in valley floor elevations that persist long after ice retreat. These hanging relationships reflect the greater erosional power of larger ice masses compared to their smaller tributary counterparts, with the depth of glacial erosion generally correlating with ice thickness and flow velocity. The resulting landscape features include spectacular waterfalls, where hanging valleys meet the main valley floor. These cascades representing permanent records of differential glacial erosion that occurred during past ice ages. What mystery governs the precise depth to which glacial erosion proceeds, creating overdeepenings and fjords that extend hundreds of meters below sea level despite originating in terrestrial mountain environments? The answer lies in the isostatic response of the crust to glacial loading, where the enormous weight of thick ice sheets depresses the underlying bedrock below its pre-glacial elevation, allowing glacial erosion to proceed to depths that would be impossible under normal circumstances. When the ice eventually retreats, the landscape gradually rebounds toward its original elevation, but the deeply eroded valleys remain as permanent features that record the maximum extent of glacial influence. Glacial striations preserve directional information about former ice flow with remarkable fidelity, their orientation and spacing providing detailed records of glacial dynamics that operated thousands of years before human observation. These erosional features resist weathering more effectively than most other geological indicators, maintaining their clarity across multiple glacial-interglacial cycles and enabling reconstruction of ice flow patterns for mountain ranges throughout the world. The systematic study of striation patterns has revealed complex histories of glacial advance and retreat that reflect orbital-scale climate variations operating over hundreds of thousands of years. Roches moutonnées demonstrate glacial erosion's ability to create asymmetric landforms that reflect the direction of ice movement, with their gentle up-valley slopes formed by abrasion and their steep down-valley faces created by plucking along joint planes and fracture systems. These streamlined bedrock knobs dot formerly glaciated landscapes like geological weather vanes, their orientation providing immediate visual evidence of former ice flow directions that operated when the climate was dramatically different from present conditions. Only took ice this long to learn that patient pressure accomplishes what sudden impacts cannot achieve, that the most effective erosion occurs through sustained contact rather than episodic violence. Only took glaciers this long to discover that their greatest sculptural power emerges from the combination of quarrying and grinding, plucking and polishing working together to create landscapes of unprecedented architectural grandeur. Only took frozen water this long to demonstrate that solid ice moves like thick honey when given sufficient time and pressure, transforming from atmospheric precipitation into Earth's most effective agent of mountain landscape modification. Roots discover the secret language of stone through chemical conversations that begin when the first hardy seeds find purchase in hairline cracks barely wide enough to admit a grain of sand. These pioneer plants, often lichens and mosses that require little more than moisture and microscopic amounts of soil to establish themselves, initiate biological processes that will continue for centuries as successive generations of increasingly larger organisms learn to exploit the weaknesses that their predecessors created in the mountain's crystalline armor. The establishment of life on bare rock represents one of nature's most patient enterprises, with each successful colonization event creating conditions that will support slightly more complex communities in an ecological succession that parallels the physical breakdown of the bedrock substrate. The mechanical force exerted by growing root systems operates through hydraulic principles that concentrate enormous pressures into spaces too small for human observation, yet large enough to accommodate the cellular expansion that drives plant growth toward light and nutrients. Tree roots can generate pressures exceeding several hundred pounds per square inch as they expand within confined spaces. Their radial growth creating stresses that propagate outward from root channels into the surrounding rock mass like slow-motion explosions that continue for decades rather than seconds. This biological wedging proves remarkably effective at propagating existing fractures, with root expansion following and widening natural joint systems until individual rock blocks become completely separated from the parent bedrock. Acidic root exudates contribute chemical erosion that operates simultaneously with the mechanical effects of root expansion, creating conditions where both physical and chemical weathering processes accelerate in the immediate vicinity of plant root systems. These organic acids, produced as byproducts of normal cellular metabolism, can achieve pH values significantly lower than natural rainfall, enabling them to dissolve minerals that resist attack by simple carbonic acid. The root-soil interface becomes a zone of enhanced chemical activity where carbonic acid, organic acids, and various chelating compounds work together to liberate ions from crystal lattices that have remained stable for millions of years in the absence of biological influences. Mycorrhizal fungi extend the reach of plant root systems through symbiotic relationships that create vast underground networks connecting individual plants into cooperative communities that share resources and chemical information. These fungal hyphae, often less than a few micrometers in diameter, can penetrate rock fractures too narrow for plant roots, carrying acids and chelating compounds deep into bedrock where they initiate weathering reactions in previously inaccessible locations. The combined effect of plant roots and their fungal partners creates three-dimensional zones of enhanced weathering that can extend several meters into solid bedrock, far beyond the reach of purely physical or chemical processes operating in the absence of biological catalysis. Succession proceeds through predictable stages as soil development creates conditions that support increasingly larger and more complex plant communities, each stage modifying the bedrock weathering environment in ways that facilitate the establishment of the next successional community. Grasses and herbs give way to shrubs, which eventually yield to forest communities where tree roots can reach depths of tens of meters into fractured bedrock. The mature forest stage represents the culmination of biological weathering processes, with large root systems creating extensive networks of fractures, while forest litter adds organic matter to surface soils that support diverse microbial communities, contributing additional chemical weathering agents. Temporal cycles in plant growth create rhythmic patterns of root expansion and decay that subject bedrock to repeated episodes of stress application and release. These biological loading cycles proving particularly effective at propagating fatigue fractures in crystalline rocks. Annual growth rings in tree roots record decades of incremental expansion within rock fractures, while seasonal variations in root activity create periodic pulses of enhanced chemical weathering that correspond to periods of maximum biological productivity. The death and decay of root systems leave behind networks of interconnected cavities that provide pathways for water infiltration and continued chemical attack long after the original vegetation has disappeared. Species-specific differences in root architecture and chemistry create distinct patterns of bedrock modification that reflect the evolutionary adaptations of different plant lineages to life on rocky substrates. Coniferous trees typically develop extensive lateral root systems that spread widely through shallow soil layers and upper bedrock fractures, while deciduous species often produce deeper taproot systems that penetrate vertically into joint systems and fault plains. These architectural differences result in characteristic fracture patterns that can persist in the bedrock long after forest succession has moved through different species compositions. Microorganisms associated with plant root systems contribute additional chemical weathering capacity through the production of specialized compounds that can complex with metal ions and facilitate mineral dissolution under conditions that would not support purely inorganic weathering reactions. Bacterial populations in the rhizosphere often exceed millions of individuals per gram of soil, their collective metabolic activity creating chemical microenvironments that differ dramatically from bulk soil conditions. These microbial communities can accelerate mineral weathering rates by factors of 10 or more compared to sterile conditions, demonstrating the profound influence of biological processes on geological transformation rates. What mystery governs the precise depth to which plant roots can penetrate solid bedrock, creating biological weathering zones that extend far beyond the obvious soil layers visible at the surface? The answer lies in the hydraulic conductivity of fractured rock masses, where existing joint systems and fault plains provide pathways for both root penetration and water movement that enable biological processes to operate at depths previously thought to be beyond the reach of surface-derived influences. Recent investigations using ground-penetrating radar and core drilling have revealed tree root systems extending more than 30 meters into bedrock, creating weathering zones of unprecedented vertical extent. Alpine plant communities demonstrate remarkable adaptations to extreme environmental conditions that enable biological weathering processes to operate even in harsh mountain environments where growing seasons may last only a few months per year. These specialized plant communities often exhibit enhanced production of organic acids and chelating compounds that compensate for the limited time available for weathering reactions, achieving in a few months what lower elevation communities accomplish over entire annual cycles. The cushion plants and mat-forming species characteristic of alpine environments create particularly intensive weathering zones where their concentrated root systems focus biological activity into small areas of bedrock. Soil development rates in newly deglaciated terrain provide insights into the timescales required for biological weathering processes to modify bedrock surfaces, with measurable soil accumulation occurring within decades of initial plant colonization. These primary succession sequences demonstrate the rapid establishment of positive feedback relationships between plant growth and soil formation, where small amounts of initial soil development enable larger plants to establish, which in turn accelerate weathering and soil production rates. The resulting exponential growth in biological weathering capacity explains how barren rock surfaces can support mature forest communities within a few centuries of initial exposure. Tree throw events, where entire root systems are exposed through windfall or other disturbances, create sudden episodes of intense bedrock exposure that reveal the extent of biological penetration into solid rock masses. These natural excavations often expose root-modified bedrock extending several meters below the surface, with rock fractures clearly widened and chemically altered by decades of biological activity. The exposed surfaces typically exhibit characteristic staining and mineral alteration patterns that distinguish biologically weathered rock from surfaces modified by purely physical or chemical processes. Only took life this long to discover that persistence grows stronger than stone, that the patient pressure of expanding cells can accomplish what sudden geological forces cannot sustain. Only took roots this long to learn that chemical warfare proves more effective than mechanical force alone, that the combination of acid production and physical expansion creates synergistic effects that exceed the sum of their individual contributions. Only took biological weathering this long to demonstrate that living systems can accelerate geological processes by orders of magnitude, transforming timescales measured in millions of years into processes observable within human lifetimes. The chemistry of forgetting begins when limestone encounters the patient acidity of groundwater, a molecular dialogue that will continue for thousands of years as carbonic acid teaches calcium carbonate to abandon its crystalline memories of ancient tropical seas. Each raindrop that seeps into soil picks up carbon dioxide from decaying organic matter and root respiration, transforming into a weak but persistent solution that finds its way through fractures and bedding planes into the limestone's carefully ordered crystal structure. This underground conversation proceeds at temperatures barely above freezing, in darkness, absolute and permanent, where chemical reactions that seem impossible at the surface operate with quiet efficiency in the hidden spaces between rock grains. Calcium carbonate dissolves through a deceptively simple reaction that masks the complexity of the molecular processes involved, as carbonic acid converts solid limestone into calcium ions and bicarbonate ions that disappear into groundwater solution without leaving visible traces of their former existence. The reaction proceeds faster in cold water than in warm, a thermodynamic peculiarity that makes high-altitude and high-latitude limestone terrains particularly susceptible to solution weathering despite their harsh climate conditions. This counterintuitive temperature dependence means that alpine limestone peaks experience more rapid chemical erosion than their tropical counterparts, dissolving into invisibility while appearing to stand unchanged against the sky. Karst landscapes develop through the systematic removal of limestone bedrock by solution processes that create underground drainage systems of remarkable complexity, their passages following bedding planes and joint systems with the precision of water seeking its inevitable level. Surface streams disappear into swallow holes and emerge miles away as major springs, their underground journeys guided by the three-dimensional architecture of soluble bedrock layers interbedded with insoluble shales and sandstones. These subterranean river systems often carry more water than their surface counterparts, creating hidden drainage networks that can extend for hundreds of kilometers through limestone aquifers. Cave formation represents the most dramatic expression of limestone solution, as groundwater flow concentrates along preferential pathways that gradually enlarge from hairline fractures into passages large enough to accommodate underground rivers. The enlargement process operates through positive feedback mechanisms, where increased flow accelerates dissolution rates, which creates larger passages that can accommodate even greater flows in a self-reinforcing cycle that continues until structural limitations or water table changes alter the hydraulic conditions. The resulting cave systems preserve detailed records of former groundwater flow patterns, their passage orientations and dimensions reflecting the hydraulic gradients that operated during their formation. Speleothems grow through the reverse of the dissolution process, as calcium-saturated groundwater releases carbon dioxide upon contact with cave atmospheres, causing calcium carbonate to precipitate in the delicate formations that decorate limestone caverns with their patient architectural experiments. Stalactites descend from cave ceilings while stalagmites rise from floors, their growth rates measured in millimeters per century as they slowly approach each other across gaps that may require thousands of years to close. These formations record climate variations in their internal chemistry, preserving isotopic signatures that reflect temperature and precipitation changes occurring on the surface far above their underground laboratories. Solution rates vary dramatically with limestone purity and crystal structure, as different varieties of calcium carbonate exhibit distinct susceptibilities to acid attack based on their geological history and mineral composition. Marble. metamorphosed from limestone under conditions of elevated temperature and pressure, often displays enhanced resistance to solution due to its recrystallized texture and reduced porosity compared to sedimentary limestone. Conversely, fossiliferous limestone containing abundant organic matter or clay impurities may dissolve more rapidly due to the presence of carbonic acid generated by bacterial decomposition of organic compounds trapped within the rock matrix. Groundwater chemistry evolves as solutions migrate through limestone aquifers, their dissolved load increasing systematically as they encounter fresh bedrock surfaces along their underground pathways. The initial contact between aggressive groundwater and limestone creates water chemistry conditions that become progressively less corrosive as calcium and bicarbonate concentrations approach saturation levels. This chemical evolution explains why the most rapid dissolution occurs in recharge areas where fresh rainwater first encounters limestone bedrock, while discharge areas often exhibit mineral precipitation rather than continued solution. Dolomite weathers through similar but more complex chemical pathways that involve the dissolution of both calcium and magnesium carbonates, creating groundwater chemistry signatures that differ significantly from pure limestone terrain. The presence of magnesium in dolomite crystal structures affects dissolution kinetics in ways that are still not completely understood, with some studies suggesting faster weathering rates, while others indicate greater resistance compared to pure limestone. These uncertainties reflect the complex interplay between crystal structure, mineral composition, and groundwater chemistry that governs carbonate dissolution under natural conditions. What mystery governs the precise geometry of cave passage development, creating underground networks that seem to follow architectural principles of remarkable sophistication despite their formation through apparently random chemical processes? The answer lies in the hydraulic optimization that occurs as groundwater flow adjusts to minimize energy expenditure, automatically developing passage configurations that maximize flow efficiency for given hydraulic gradients. These self-organizing properties create cave systems that exhibit fractal characteristics, with passage networks repeating similar patterns at multiple scales throughout the limestone aquifer. Blind valleys and dry valleys preserve evidence of former surface drainage that has been captured by developing cave systems, their abandoned channels marking the transition from surface to subsurface drainage as limestone solution progresses from initial fracture enlargement to mature karst development. These relict features demonstrate the systematic migration of drainage from surface streams to underground conduits, a process that can occur over timescales of thousands rather than millions of years in regions of rapid limestone dissolution. The resulting landscape evolution creates terrain where surface topography provides misleading information about actual water flow patterns and erosional processes. Tufa deposits form where limestone-saturated groundwater emerges at springs and waterfalls. The rapid degassing of carbon dioxide upon surface exposure, causing immediate precipitation of calcium carbonate in delicate formations that can build impressive terraces and dams across stream channels. These deposits often incorporate plant material and organic debris, creating fossilized records of vegetation communities that existed during periods of active tufa formation. The resulting limestone formations can achieve growth rates of centimeters per year under optimal conditions, demonstrating that limestone formation continues in modern environments despite the general predominance of dissolution over precipitation in most carbonate terrains. Isotopic signatures in dissolved limestone preserve information about climate conditions during solution, as the carbon and oxygen isotope ratios in carbonic acid reflect atmospheric composition and temperature conditions at the time of groundwater recharge. These chemical fingerprints enable reconstruction of paleoclimate conditions from cave formations and spring deposits, creating detailed records of environmental change that span thousands of years with resolution approaching seasonal variations. The resulting paleoclimate archives often provide the most complete available records of terrestrial climate variations for regions where other proxy indicators are poorly preserved. Only took limestone this long to learn that memory dissolves more easily than stone, that the chemical records of ancient seas prove vulnerable to the patient work of slightly acidic groundwater. Only took carbonic acid this long to discover that persistence accomplishes what concentration cannot achieve, that weak solutions applied over geological time prove more effective than strong acids applied briefly. Only took karst this long to demonstrate that the most dramatic landscapes often develop through invisible processes, that underground rivers can create more impressive architecture than their surface counterparts through the simple act of teaching stone to forget its solid existence. Wind learns the art of geological conversation through its 10-million-year apprenticeship with dust, beginning each lesson as invisible atmospheric motion and ending as a carrier of microscopic particles that represent the molecular signatures of distant mountain ranges. The relationship between moving air and solid rock operates through principles of fluid dynamics that seem almost gentle in their application, yet prove devastating in their cumulative effects across the vast timescales required for aeolian processes to complete their patient work of landscape modification. Each gust of wind that sweeps across exposed bedrock surfaces lifts particles measured in micrometers, transporting them through the atmosphere in suspended loads that can travel thousands of kilometers before settling in ocean basins or accumulating in terrestrial sedimentary deposits. Saltation governs the movement of sand-sized particles through a bouncing motion that transfers energy from wind to surface materials through impacts that occur millions of times per second across active erosional surfaces. Individual grains leap into the airstream where they travel short distances before gravity returns them to the surface with sufficient kinetic energy to dislodge additional particles upon impact, creating cascade effects that can mobilize entire sand sheets during high-velocity wind events. This mechanical process operates most efficiently when wind speeds exceed threshold velocities that vary with particle size and surface roughness, creating conditions where modest increases in atmospheric motion can trigger dramatic increases in sediment transport rates. Abrasion occurs when wind-transported particles impact exposed rock surfaces with velocities that enable them to chip away microscopic fragments from even the most resistant minerals. This process, proving particularly effective at altitudes where atmospheric density decreases and wind velocities increase due to reduced frictional drag. Quartz grains suspended in high-velocity winds act like atmospheric sandpaper, gradually wearing away feldspar crystals and other susceptible minerals, while themselves becoming progressively more rounded through collisions with both bedrock surfaces and other transported particles. The effectiveness of this aeolian abrasion depends critically on the hardness differential between the abrading particles and the target surfaces, with silica-rich sediments proving capable of eroding almost any bedrock type given sufficient time and wind energy. Deflation removes fine-grained sediments from exposed surfaces through the systematic lifting and transport of particles small enough to remain suspended in atmospheric turbulence for extended periods, often measured in days or weeks for the finest clay-sized materials. This selective removal process gradually concentrates coarser particles at the surface while transporting finer fractions to distant depositional environments, creating lag deposits of resistant materials that armor the underlying bedrock against continued erosional attack. Desert pavements develop through this selective deflation process, their closely packed surfaces of wind-polished stones creating conditions that actually reduce further erosion by protecting underlying sediments from direct wind attack. Atmospheric circulation patterns determine the regional effectiveness of wind erosion through the establishment of persistent pressure gradients that create predictable patterns of high-velocity airflow across specific geographic regions. Mountain ranges generate orographic effects that accelerate winds on their windward slopes while creating lee-side areas of reduced wind energy. These variations in atmospheric velocity creating systematic patterns of erosion and deposition that persist for thousands of years. The resulting landscape modifications often exhibit clear directional asymmetries that reflect the prevailing wind patterns operating during their formation, with windward slopes showing evidence of enhanced erosion, while leeward areas accumulate wind-transported sediments. Dust storms represent episodic events of intense aeolian activity that can accomplish decades of normal wind erosion within the span of a few hours. Their massive sediment loads creating atmospheric conditions that reduce visibility to near zero while transporting millions of tons of surface materials across continental distances. These events often originate in arid regions where sparse vegetation provides little protection against wind erosion. But their effects extend far beyond their source areas as atmospheric circulation systems carry dust loads across ocean basins and deposit them in regions thousands of kilometers from their points of origin. The global distribution of wind-transported sediments creates chemical and isotopic signatures in marine and terrestrial deposits that preserve detailed records of past atmospheric circulation patterns and aridity variations. Ventifacts form through the systematic abrasion of individual rocks by wind-transported particles. Their characteristic faceted surfaces and polished textures providing clear evidence of prolonged exposure to high-velocity winds carrying abrasive sediment loads. These wind-sculpted stones often exhibit multiple facets that record changes in prevailing wind directions over time, their orientations providing paleoclimatic information about former atmospheric circulation patterns. The development of ventifact surfaces requires thousands of years of consistent wind abrasion, making them reliable indicators of long-term aridity and atmospheric circulation stability. Low-S deposits accumulate through the systematic deposition of wind-transported silt-sized particles in areas where atmospheric turbulence decreases sufficiently to allow sediment settling. These aeolian sediments, often achieving thicknesses of hundreds of meters in regions downwind from major dust source areas. The Low-S Plateau of northern China represents one of the world's most extensive examples of wind-deposited sediments. Its layered deposits preserving detailed records of atmospheric circulation and climate variations spanning the past several million years. These sequences provide some of the most complete available records of continental climate change, their alternating layers of different composition reflecting systematic variations in dust source areas and transport pathways. What mystery governs the precise size distribution of particles that wind can transport effectively, creating characteristic patterns of sediment sorting that distinguish aeolian deposits from those formed by water or ice? The answer lies in the relationship between particle settling velocity and atmospheric turbulence intensity, where only particles small enough to remain suspended in available updrafts can be transported significant distances from their source areas. This aerodynamic sorting creates distinctive textural signatures in wind-transported sediments, with modal grain sizes typically falling within narrow ranges that reflect the fluid dynamic properties of atmospheric transport systems. Yardangs develop through the systematic erosion of bedrock by persistent unidirectional winds, their streamlined shapes reflecting the aerodynamic optimization that occurs as rock masses adjust their geometry to minimize resistance to atmospheric flow. These wind-sculpted ridges can achieve lengths of several kilometers while maintaining remarkably consistent orientations that parallel the prevailing wind directions operating during their formation. The internal structure of yardangs often reveals systematic patterns of joint exploitation and differential erosion that reflect variations in rock resistance and fracture spacing, creating natural laboratories for studying the interaction between atmospheric processes and geological structures. Atmospheric dust loading affects global climate through complex feedback mechanisms that involve both radiative forcing and cloud nucleation processes, creating connections between local erosional events and global atmospheric circulation patterns. Dust particles suspended in the upper atmosphere can alter regional temperature patterns by absorbing and scattering solar radiation, while also serving as condensation nuclei that influence cloud formation and precipitation patterns. These atmospheric connections mean that wind erosion in one region can influence climate conditions thousands of kilometers away, creating global-scale linkages between geological processes and atmospheric dynamics. Aeolian processes operate with particular intensity in arid and semi-arid environments where sparse vegetation provides minimal protection against wind erosion, but they also contribute to landscape modification in humid regions during periods of drought or vegetation disturbance. Glacial outwash plains often experience intense wind erosion during periods when vegetation has not yet colonized recently exposed sediments, creating conditions where large quantities of glacially derived materials become available for atmospheric transport. These periglacial wind systems can create extensive loess deposits that preserve records of former ice sheet positions and glacial climate conditions. Only took wind this long to learn that patience moves mountains more effectively than violence, that the systematic transport of microscopic particles accomplishes landscape modification on scales that exceed the effects of dramatic storm events. Only took atmospheric circulation this long to discover that persistence creates power, that modest but consistent particle transport can eventually relocate entire mountain ranges grain by grain across continental distances. Only took 10 million years for wind to demonstrate that invisible forces often prove more effective than obvious ones, that the subtle art of particle lifting and transport can reshape continents through the accumulation of countless individual acts of geological conversation. The isostatic sigh emerges from deep within the Earth's mantle as a slow exhalation of relief. The plastic rock layers beneath the disappearing mountain adjusting their configuration like a sleeping giant turning over after carrying an enormous burden for millions of years. As erosion systematically removes mass from the mountain's summit and flanks, reducing its gravitational load on the underlying crust, the viscous mantle material that was displaced downward during the peak's original formation begins its patient journey back toward equilibrium. This vertical adjustment operates through principles of buoyancy that govern the flotation of continents on the denser mantle substrate, each ton of eroded rock triggering a proportional upward movement of the mountain's remaining foundation as isostatic forces work to restore gravitational balance. The mathematics of isostatic adjustment follow predictable ratios that reflect the density contrast between crustal rocks and the underlying mantle material, with approximately 4 meters of erosional removal triggering 1 meter of compensatory uplift as the lighter continental crust rises through the denser mantle like a cork bobbing upward in water after a weight has been removed from its surface. This mechanical response operates with time constants measured in thousands of years, as the mantle's high viscosity prevents rapid adjustment to changing surface loads despite the enormous forces involved in isostatic equilibration. The resulting landscape evolution creates the paradoxical situation where mountains continue to rise even as erosion removes material from their peaks, their elevation decreasing more slowly than simple erosion rates would predict. Crustal roots extend deep into the mantle beneath major mountain ranges, these downward projections of continental material creating gravitational anomalies that can be detected by sensitive instruments long after the surface topography has been reduced to rolling hills. The principle of isostatic compensation requires that elevated topography be balanced by crustal thickening that extends the mountain's mass downward into the mantle, creating routes that can reach depths of 60 kilometers or more beneath the highest peaks. As erosion proceeds and surface elevation decreases, these routes gradually rise through the mantle like enormous icebergs, adjusting their flotation level as their above-water portions are systematically removed. Rebound rates vary with the size and loading history of eroding mountain ranges, with larger masses producing more pronounced isostatic effects that continue for millions of years after the complete removal of surface topography. Scandinavia continues to rise at rates of several millimeters per year as a result of isostatic adjustment to the removal of ice sheets that disappeared more than 10,000 years ago, demonstrating the long-time constants involved in crustal equilibration processes. These ongoing vertical movements affect everything from sea level measurements to the flow directions of rivers, creating dynamic landscapes where the solid Earth itself participates in the erosional process through its mechanical response to changing surface loads. Flexural rigidity of the lithosphere determines the spatial extent over which isostatic adjustments occur, with the elastic properties of the outermost solid shell controlling whether rebound remains localized beneath eroding areas or spreads across broad regions through flexural coupling effects. The lithosphere behaves like a thin, elastic plate floating on a viscous substrate, its bending characteristics determining how loads and load changes are transmitted through the crustal structure. Narrow mountain ranges produce localized isostatic effects, while broad uplands create regional flexural responses that can influence topography hundreds of kilometers from the actual erosional source areas. Peripheral bulges develop around regions of rapid isostatic rebound as the mantle material displaced upward beneath rebounding areas flows laterally outward and creates compensatory downwarping in surrounding regions. These secondary effects often producing subsidence rates comparable to the rebound rates occurring in the central areas. The Hudson Bay region of Canada exhibits such peripheral effects related to ongoing rebound from ice sheet removal, with areas around the bay's margins experiencing relative subsidence while the central region continues to rise. These regional patterns of vertical movement create complex drainage adjustments and shoreline changes that persist for thousands of years after the initial cause of isostatic disequilibrium has been removed. Erosional unloading can trigger secondary geological processes, including volcanism and seismic activity, as the changing stress fields associated with isostatic adjustment alter the mechanical conditions within the crust and upper mantle. The removal of large surface loads reduces confining pressure on underlying rock masses, potentially enabling partial melting or fault movement that would not occur under fully loaded conditions. Some volcanic provinces show clear relationships between periods of rapid erosional unloading and increased igneous activity, suggesting that isostatic processes can influence magma generation and transport through stress-dependent mechanisms. Marine terraces preserve evidence of former isostatic equilibrium positions in coastal mountain ranges, their elevation sequences recording the complex interplay between erosional unloading, crustal rebound, and sea level variations that operated during their formation. These wave-cut platforms often occur at elevations hundreds of meters above current sea level, their positions reflecting the cumulative effects of both tectonic uplift and isostatic adjustment over periods of hundreds of thousands of years. The systematic study of marine terrace sequences provides detailed information about vertical movement rates and their temporal variations in tectonically active coastal regions. What mystery governs the precise timing of isostatic responses to erosional unloading, creating delays between cause and effect that can span thousands of years despite the enormous forces involved in crustal equilibration? The answer lies in the rheological properties of mantle materials under the temperature and pressure conditions that exist at depths of hundreds of kilometers. where solid rock behaves like an extremely viscous fluid with flow characteristics that depend on both stress magnitude and application duration. The mantle's effective viscosity under isostatic loading conditions exceeds that of any surface material by many orders of magnitude, creating response times that are long even by geological standards. Gravity anomalies associated with isostatic disequilibrium can persist for millions of years after the removal of surface topography, as the slow adjustment of crustal roots to changing surface loads creates mass distributions that differ from perfect isostatic equilibrium. These gravitational signatures provide insights into the long-term evolution of mountain ranges and the deep crustal structure that underlies even relatively subdued topography. Modern satellite gravimetry can detect these subtle mass anomalies with sufficient precision to reconstruct the former positions and magnitudes of mountain ranges that disappeared tens of millions of years ago. Metamorphic core complexes form in some mountain ranges through the interaction between erosional unloading and extensional tectonics. As the removal of surface loads enables the upward movement of deep crustal rocks that record high temperature and high pressure conditions during their formation, these geological structures provide direct access to rocks that formed at depths of 20 kilometers or more. Their mineral assemblages and structural characteristics preserving detailed records of the pressure-temperature-time paths that operated during mountain building and subsequent erosional exhumation. The exposure of such deep-level rocks requires both rapid erosion and significant isostatic adjustment working together over periods of several million years. Denudation rates calculated from cosmogenic isotope concentrations in river sediments often exceed apparent topographic lowering rates due to the compensatory effects of isostatic rebound, creating situations where mountains lose elevation more slowly than their erosion rates would suggest. This phenomenon demonstrates the importance of considering deep earth processes when interpreting surface erosional phenomena, as the mechanical coupling between erosion and isostatic adjustment significantly modifies the relationship between sediment production rates and topographic evolution. The resulting discrepancies between erosion rates and apparent landscape lowering can reach factors of 2 to 3 in rapidly eroding mountain ranges. Only took isostatic adjustment this long to discover that rising and falling operate as coupled processes, that the removal of surface loads inevitably triggers compensatory movements in the deep earth that partially counteract the effects of erosion. Only took mountains this long to learn that their foundations possess memory, that the mantle remembers former loading conditions and responds to unloading with movements that can continue for millions of years. Only took geology this long to realize that the Earth sighs when mountains disappear, exhaling slowly through vertical movements that represent the planet's mechanical response to the systematic redistribution of mass from high elevations to ocean basins. Sediments remember the summit in their chemical fingerprints and mineral compositions, carrying encrypted messages of altitude and stone across vast distances as they journey from highland sources to oceanic depositional basins through the patient transport systems of rivers, winds, and glacial ice. Each grain of quartz bears witness to the crystalline environment of its birth deep within plutonic chambers, while feldspar fragments preserve isotopic signatures that record the age and thermal history of the granitic intrusions from which they weathered. Clay particles maintain molecular memories of the specific weathering conditions that transformed their parent minerals. Their crystal structures, encoding information about temperature, pH, and chemical composition of the solutions that facilitated their formation through hydrolysis reactions in highland soils. Provenance analysis reveals the geographic origins of sedimentary particles through systematic comparison of their mineral assemblages, chemical compositions, and isotopic characteristics with potential source regions, creating detailed maps of sediment transport pathways that operated millions of years in the past. Zircon crystals prove particularly valuable for this detective work, as their uranium-lead isotopic systems remain stable through multiple cycles of weathering, transport, and deposition, preserving radiometric ages that directly link sedimentary deposits to specific igneous source rocks. These microscopic time capsules can survive multiple episodes of erosion, transport, and redeposition, carrying their original crystallization ages through complex sedimentary cycles that may span hundreds of millions of years. Heavy mineral suites provide additional clues about sediment provenance through their distinctive assemblages of resistant accessory minerals that reflect the specific igneous, metamorphic, or sedimentary environments where they formed. Garnet, tourmaline, and rutile grains each carry diagnostic chemical signatures that can be matched to particular geological terrains, while their relative abundances reflect the erosional history and transport distances involved in their delivery to depositional basins. The systematic downstream changes in heavy mineral compositions record the progressive mixing of sediments from multiple source areas as tributary streams contribute their own distinctive mineral assemblages to major river systems. Geochemical weathering indices calculated from the major element chemistry of sedimentary rocks preserve quantitative information about the intensity of chemical weathering that operated in their source regions, with ratios such as the chemical index of alteration providing numerical measures of the degree to which primary minerals were converted to clay minerals during soil formation processes. These chemical proxies enable reconstruction of paleoclimate conditions in ancient mountain ranges, as weathering intensity correlates strongly with temperature and precipitation patterns that controlled soil formation rates in highland source areas. The resulting paleoclimatic records often provide the only available information about environmental conditions in mountain ranges that have long since been completely eroded away. Detrital thermochronology reconstructs the thermal history of sediment source regions through analysis of temperature-sensitive isotopic systems in individual mineral grains, creating detailed records of the cooling and exhumation pathways that brought deep crustal rocks to the surface where they became available for erosional attack. Apatite fission track ages record the timing of cooling through temperatures around 60 degrees Celsius, while UTH, Richie, he ages in zircon, preserve information about even lower temperature cooling events that occurred during the final stages of exhumation. These thermal histories can be inverted to calculate erosion rates and surface uplift patterns that operated in source regions millions of years before the sediments were deposited. Sediment flux variations preserved in stratigraphic sequences record temporal changes in erosion rates and sediment supply that reflect tectonic, climatic, and geological controls operating in highland source areas over timescales ranging from thousands to millions of years. Thick, coarse-grained sequences often mark periods of rapid uplift and enhanced erosion, while fine-grained intervals may record either tectonic quiescence or climatic conditions that reduced erosional efficiency in source regions. The grain size distributions and sedimentary structures preserved in these deposits provide additional information about transport mechanisms and depositional environments that link highland erosion to basin sedimentation through complex cause and effect relationships. Turbidite systems transport mountain-derived sediments across continental shelves and into deep ocean basins through episodic gravity flows that can carry enormous volumes of terrigenous material thousands of kilometers from their continental sources in single depositional events. These submarine avalanches often preserve detailed records of highland geology in their mineral compositions and geochemical signatures, creating deep-sea archives of continental erosion that can extend back hundreds of millions of years. The systematic analysis of turbidite compositions in ancient deep-sea fan deposits provides insights into the geological evolution of mountain ranges that may have completely disappeared from the continental record. Cosmogenic isotope concentrations in sediments provide direct measurements of the residence times that sedimentary particles spent at or near the Earth's surface before their incorporation into depositional sequences. These exposure ages reflecting the efficiency of erosional processes and the transport times involved in moving material from source to sink. Beryllium-10 and aluminum-26 isotopes accumulate in quartz grains through bombardment by cosmic ray particles, their concentrations recording the duration of surface exposure with temporal resolution that can distinguish between rapidly eroding, tectonically active regions and slowly eroding stable cratons. These measurements enable quantitative reconstruction of erosion rates operating in source regions during specific time intervals preserved in the sedimentary record. What mystery governs the selective preservation of certain mineral species through multiple cycles of weathering and transport, while others disappear completely during their first encounter with surface conditions? The answer lies in the thermodynamic stability relationships between different crystal structures and the chemical conditions that characterize surface environments, where minerals formed under high temperature and high pressure conditions prove most susceptible to alteration when exposed to low temperature aqueous solutions. Quartz achieves remarkable stability under surface conditions due to the strength of its silicon-oxygen bonds, while feldspars succumb readily to hydrolysis reactions that convert them to clay minerals and dissolved ions. Paleogeographic reconstructions based on sediment provenance data enable detailed mapping of ancient drainage systems and highland basin relationships that operated during specific time intervals preserved in the geological record. These studies, revealing systematic changes in sediment transport pathways that reflect evolving tectonic configurations and topographic development. The direction and magnitude of sediment transport often preserve the only available information about the orientation and elevation of mountain ranges that have since been completely removed by erosion. Their former existence recorded only in the compositional characteristics of their erosional products. Mudstone geochemistry provides high-resolution records of average upper crustal composition that reflect the systematic mixing of sediments from diverse source regions over the large geographic areas drained by major river systems. These fine-grained deposits integrating chemical signals from entire mountain ranges into representative samples of continental weathering products. The trace element signatures preserved in ancient mudstones enable reconstruction of the tectonic settings and geological compositions of their source regions, while their isotopic characteristics provide information about the crustal evolution and mantle crust differentiation processes that operated during earlier phases of Earth history. Sandstone petrography reveals the tectonic settings of ancient mountain ranges through systematic analysis of framework grain compositions. As different plate tectonic environments produce characteristic mineral assemblages that reflect their distinctive igneous, metamorphic, and sedimentary source rock types, volcanic arc settings generate sediments rich in plagioclase feldspar and volcanic lithic fragments, while continental collision zones produce quartzose sandstones with abundant metamorphic lithic components and K-feldspar grains derived from granitic batholiths. These compositional signatures often provide the most reliable information available about the tectonic evolution of ancient mountain-building episodes. Only took sediments this long to become libraries of mountain memory, preserving in their mineral grains and chemical compositions the detailed stories of highlands that vanished millions of years before human observation began. Only took erosional products this long to learn that travel preserves identity, that the journey from mountain peak to ocean basin can span thousands of kilometers and millions of years while maintaining the chemical fingerprints that record their highland origins. Only took geological detective work this long to discover that sedimentary rocks serve as archives of vanished topography, their compositional characteristics providing the primary evidence for mountain ranges that exist now only in the chemical memory of their erosional descendants. The unconformity's honest gap speaks with the clarity of missing time, its surface representing a geological pause in the normally continuous accumulation of sedimentary layers where millions of years have been compressed into a single contact between rocks that record dramatically different chapters in Earth's patient narrative. This erosional boundary cuts across older rock formations with the surgical precision of deep time, removing entire sequences of strata that once preserved the detailed history of ancient mountain ranges and their surrounding basins. Where continuous deposition should reveal layer upon layer of accumulated sediment, the unconformity presents instead a surface of profound absence, its existence marking intervals when erosion dominated over sedimentation and the geological record became subtraction rather than addition. Angular unconformities record episodes of mountain building followed by erosional destruction with particular clarity. Their tilted lower sequences preserving evidence of tectonic deformation, while their horizontal upper layers document the eventual planation of the deformed terrain and the resumption of sedimentary deposition across the eroded surface. The angular discordance between these rock sequences measures the magnitude of structural deformation that occurred during the missing time interval, while the depth of erosional truncation indicates the amount of material removed before deposition resumed. These relationships enable quantitative reconstruction of ancient topographic relief and erosional unroofing that operated during intervals completely absent from the preserved geological record. Disconformities represent more subtle gaps in the sedimentary record where parallel rock layers are separated by erosional surfaces that mark intervals of non-deposition or erosional removal without significant structural deformation. These boundaries often appear deceptively minor in outcrop exposures, their recognition requiring detailed analysis of fossil assemblages, radiometric ages, or stratigraphic relationships that reveal the temporal discontinuity between adjacent rock units. The missing time represented by disconformities can span millions of years despite the apparent conformable relationship between the bounding rock sequences, their existence highlighting the episodic nature of sedimentary preservation and the numerous gaps that characterize even the most complete geological sections. Paraconformities mark time gaps where erosional surfaces occur within otherwise conformable sequences, their recognition depending entirely on paleontological or geochronological evidence rather than obvious physical characteristics visible in rock exposures. These cryptic unconformities often preserve evidence of subtle erosional episodes that removed portions of the sedimentary record without creating obvious angular relationships or erosional relief. Their detection requiring sophisticated analytical techniques that can identify missing time intervals through absent fossil zones or isotopic age discontinuities. The widespread occurrence of paraconformities throughout sedimentary sequences demonstrates that the geological record contains far more gaps than complete intervals, with preservation representing the exception rather than the rule in sedimentary systems. Nonconformities document the most dramatic temporal gaps in geological sequences, where sedimentary rocks rest directly upon much older igneous or metamorphic basement complexes that represent the deeply eroded roots of ancient mountain ranges. These profound unconformities often separate rock sequences that differ in age by hundreds of millions of years, their surfaces marking the complete removal of entire orogenic systems and their subsequent burial beneath younger sedimentary deposits. The basement rocks exposed beneath nonconformities often preserve evidence of multiple episodes of mountain building, metamorphism, and erosional destruction that preceded the deposition of the overlying sedimentary cover. Paleoweathering profiles developed on unconformity surfaces provide direct evidence of the sub-aerial exposure and chemical alteration that occurred during the erosional intervals represented by these temporal gaps. lateritic soils, bauxite deposits, and other indicators of intense tropical weathering often cap unconformity surfaces, their mineral assemblages and chemical compositions recording the climatic conditions that operated during the missing time intervals. These paleosols represent the only preserved evidence of surface conditions during erosional periods, their characteristics providing insights into paleoclimate, vegetation, and weathering processes that operated in environments completely absent from the normal sedimentary record. Karst development on limestone unconformity surfaces creates three-dimensional networks of solution cavities and caves that record the hydrological and chemical conditions operating during subaerial exposure intervals. These paleokarst systems often become filled with younger sediments or minerals that preserve detailed records of cave development and subsequent burial. Their internal structures providing information about groundwater flow patterns and solution processes that operated during the unconformity forming interval. The recognition of paleokarst features enables reconstruction of ancient water table positions and surface topography that existed during periods of erosional dominance. Regolith development during unconformity formation creates thick zones of weathered and altered rock that preserve evidence of the physical and chemical processes that operated during long intervals of subaerial exposure. These weathering profiles often extend tens of meters into the underlying bedrock, their mineral transformations and chemical alterations recording the progressive breakdown of primary minerals under surface conditions. The thickness and intensity of regolith development provides quantitative information about the duration and effectiveness of weathering processes that operated during unconformity formation. What mystery governs the selective preservation of unconformity surfaces, while the vast majority of erosional episodes leave no permanent record in the geological column? The answer lies in the specific combination of tectonic, eustatic, and climatic conditions required to create surfaces that survive subsequent burial and lithification, with most erosional intervals being either too brief to create recognizable boundaries or occurring under conditions that prevent their preservation in the stratigraphic record. The unconformities that do survive represent unusual circumstances where erosional surfaces were rapidly buried and protected from further modification, creating permanent archives of otherwise transient geological processes. Fossil assemblages across unconformity surfaces often show dramatic changes that reflect the evolutionary developments that occurred during the missing time intervals. These biological discontinuities providing independent evidence for the temporal significance of erosional boundaries even when physical evidence is ambiguous. The magnitude of faunal and floral changes across unconformities often correlates with the duration of the represented time gap, as longer intervals of non-preservation allow for more extensive evolutionary modification of biological communities. These paleontological relationships enable estimation of missing time intervals even when radiometric dating techniques are not applicable to the bounding rock units. Sedimentary fill of paleovalleys cut into unconformity surfaces preserves evidence of the topographic relief that existed during erosional intervals. These ancient drainage systems often providing the only direct information about the landscapes that developed during periods of dominantly erosional activity. The depth and orientation of paleovalleys record the hydraulic gradients and drainage patterns that operated during unconformity development, while their sedimentary fill documents the environmental conditions that existed during the early stages of renewed deposition. These features create three-dimensional archives of ancient topography that would otherwise be completely absent from the geological record. Regional mapping of unconformity surfaces reveals systematic patterns of erosional truncation that record the three-dimensional geometry of ancient landscapes, their elevation variations and structural relationships providing detailed information about the topographic development and subsequent erosional destruction of mountain ranges that may be completely absent from the preserved geological record. The regional extent and characteristics of major unconformities often define fundamental boundaries in geological classification systems. Their recognition marking transitions between major phases of Earth history characterized by different tectonic, climatic, and biological conditions. Hydrocarbon exploration relies heavily on unconformity mapping for understanding subsurface geological relationships, as these erosional surfaces often control fluid migration pathways and reservoir development in sedimentary basins. The petroleum industry has developed sophisticated techniques for recognizing and mapping unconformities in subsurface data, their economic importance driving detailed studies of erosional relationships that might otherwise receive limited attention in academic research. These commercial applications have contributed significantly to understanding of unconformity development and preservation in ancient sedimentary systems. Only took unconformities this long to become honest witnesses to mountain destruction, preserving in their erosional surfaces the evidence that entire mountain ranges once stood where only their absence now remains. Only took geological time this long to demonstrate that gaps speak louder than presence, that the missing chapters in Earth's stratigraphic record often tell more compelling stories than the preserved intervals. Only took erosion this long to learn how to write its signature in stone, creating permanent boundaries that mark the systematic removal of previous geological narratives and their replacement with the patient testimony of geological absence. When only roots remain, they emerge as gentle hills that betray no hint of their former alpine grandeur, their rounded summits and subdued slopes offering little evidence that they once served as the deep foundations of peaks that towered 6 kilometers above sea level and caught the morning light on crystalline faces that reflected the passage of geological ages. These humble remnants represent the final exposure of plutonic cores that crystallized 20 kilometers beneath the Earth's surface during the mountain's youth. Their coarse-grained textures recording the leisurely cooling history of magma chambers that took millions of years to solidify in the insulated depths of thickened continental crust. The granite batholiths and metamorphic complexes that now form rolling highlands once provided structural support for mountain ranges whose erosional products now rest in sedimentary basins thousands of kilometers away. Exhumation rates calculated from thermochronological data reveal the systematic unroofing that brought these deep-seated rocks to the surface through the patient removal of overlying material, their cooling ages recording the precise timing of their passage through specific temperature intervals, as erosion gradually reduced the thickness of their insulating cover. Apatite fission track ages often cluster around specific time intervals that mark episodes of accelerated erosion, while zircon-helium ages preserve evidence of even earlier cooling events that occurred when the rocks first approached the surface after their initial formation at depth. These thermal histories create detailed chronologies of landscape denudation that span tens of millions of years and document erosion rates that often exceed several hundred meters per million years during peak unroofing episodes. Metamorphic grade variations within exposed root complexes preserve evidence of the thermal and pressure conditions that existed at different levels within the original mountain structure. Their mineral assemblages recording the systematic changes in temperature and pressure that occurred with depth during the peak metamorphic episode. Sillimanite-bearing gneisses mark zones that experienced temperatures exceeding 600 degrees Celsius, while lower-grade assemblages containing biotite and chlorite record shallower crustal levels where temperatures remained below 400 degrees. The vertical sequence of metamorphic zones now exposed at the surface provides a cross-sectional view through the deep structure of the vanished mountain range. Migmatites represent the deepest exposed levels of mountain root systems, their partially melted textures recording conditions where temperatures exceeded the solidus of common crustal rock compositions, and anatexis began to generate granitic melts within the solid framework of pre-existing metamorphic rocks. These mixed rocks preserve evidence of the thermal conditions that existed in the lower crust during mountain building episodes. Their leucosome veins and restite assemblages documenting the complex interplay between solid-state deformation and partial melting that characterizes the deep levels of major orogenic systems. The presence of migmatites at the surface indicates erosional removal of at least 15 to 20 kilometers of overlying crustal material. Structural relationships within mountain root complexes reveal the intense deformation that accompanied their formation, with complex fold patterns and fault systems recording the compressional and extensional episodes that shape the deep architecture of the vanished mountain range. Shear zones often cut through these ancient structures, their myelinitic textures preserving evidence of the ductile flow that occurred at elevated temperatures and pressures during the later stages of orogenic development. The orientation and kinematics of these structural features provide information about the stress fields and deformation mechanisms that operated during mountain building, even though the surface expression of these processes has long since been removed by erosion. Plutonic suites within mountain roots record the magmatic history of the vanished origin through their compositional variations and intrusive relationships. These igneous bodies representing the frozen remnants of magma chambers that fed volcanic systems, whose surface expressions disappeared millions of years ago. Compositional zoning within individual plutons often preserves evidence of fractional crystallization and magma mixing processes that operated during their emplacement, while the overall chemical evolution of plutonic suites records systematic changes in magma generation and crustal contamination that occurred throughout the orogenic cycle. The ages and compositions of these intrusive rocks provide crucial information about the thermal and chemical evolution of the mountain building process. Ore deposits associated with mountain root complexes often represent the only preserved evidence of the hydrothermal systems that operated during the final stages of orogenic development, their mineral assemblages and alteration patterns recording the circulation of metal-bearing fluids through the cooling plutonic infrastructure. Porphyry copper deposits, skarn assemblages, and epithermal precious metal concentrations mark specific levels within the former mountain structure where fluid flow, temperature, and chemical conditions combine to create economically significant mineral concentrations. The vertical distribution of these ore deposit types provides information about the depth relationships and thermal structure that characterize the active magmatic system. Erosional landscapes developed on mountain root terrains often exhibit distinctive geomorphological characteristics that reflect the structural and compositional heterogeneity inherited from their deep crustal origins. Differential erosion along contacts between rock units of varying resistance creates systematic topographic patterns where more resistant lithologies form ridges, while less resistant units are preferentially eroded into valleys. The resulting landscape grain often preserves the structural trends and lithological boundaries that define the deep architecture of the vanished mountain range, creating surface patterns that provide insights into subsurface geological relationships. What mystery governs the precise level of erosional truncation that determines which portions of ancient mountain systems survive as exposed root complexes, while deeper levels remain buried and shallower levels are completely removed? The answer lies in the complex interplay between erosion rates, isostatic adjustment, and tectonic processes that control the three-dimensional evolution of mountain ranges over geological time, with the final level of erosional exposure depending on factors including climate history, base level changes, and regional tectonic stability that operated throughout the post-orogenic period. Geochronological studies of mountain root complexes often reveal complex thermal histories, with multiple cooling and reheating events that reflect episodic burial and exhumation during post-orogenic tectonic evolution. These thermochronological signatures demonstrate that the exposure of deep crustal rocks often involves multiple phases of unroofing separated by periods of relative stability or even renewed burial, creating complex age patterns that require sophisticated analytical techniques to unravel. The resulting thermal histories provide detailed information about the long-term tectonic evolution of continental crust in post-orogenic settings. Paleomagnetic studies of exposed mountain roots preserve records of continental drift and rotational motions that occurred during their transport from their original positions to their current locations. These magnetic signatures, often providing the only available information about the paleogeographic evolution of ancient orogenic systems. The magnetic inclinations and declinations recorded in root-complex rocks often differ significantly from those expected for their current latitudes, indicating substantial latitudinal transport and rotational motion that occurred during post-orogenic continental drift. These paleomagnetic constraints enable reconstruction of ancient continental configurations and plate motions. Fluid inclusion studies in minerals from mountain root complexes preserve direct samples of the aqueous and carbonic fluids that circulated through the deep crust during orogenic development. Their compositions and homogenization temperatures providing quantitative information about the pressure-temperature conditions and fluid chemistry that characterized metamorphic and magmatic processes at depth. These microscopic fluid samples often represent the only available direct evidence of the chemical conditions that operated in the deep levels of ancient mountain systems, their preservation enabling detailed reconstruction of fluid-rock interaction processes that occurred at depths now accessible only through erosional exposure. Cosmogenic isotope concentrations in surfaces within mountain root terrains provide quantitative constraints on erosion rates and landscape evolution timescales that characterize the final stages of mountain degradation. These exposure ages recording the duration of surface exposure since exhumation of the deep crustal rocks. The systematic variation of cosmogenic ages across different elevations and rock types within root complexes enables calculation of denudation rates and topographic evolution patterns that operated during the transition from active orogenic landscapes to stable cratonic platforms. Only took mountain roots this long to become the final witnesses to vanished alpine grandeur, preserving in their crystalline memory the thermal and structural records of peak elevations that once rivaled the modern Himalayas in their vertical reach toward ancient skies. Only took deep crustal rocks this long to learn patience in their journey toward the surface, their slow exhumation requiring tens of millions of years to bring magma chamber floors into contact with atmospheric weathering. Only took erosion this long to teach mountains humility, reducing proud alpine peaks to gentle hills that reveal the truth that even the deepest foundations eventually yield to the patient arithmetic of geological time. The next mountain dreams in the slow convergence of tectonic plates thousands of kilometers away, where ocean floor spreads outward from mid-oceanic ridges with the patience of fingernails growing in the darkness, carrying continents toward their inevitable collision across vast expanses of deep time that dwarf human comprehension of geological process. Somewhere beneath an ocean that has been narrowing for 50 million years, basaltic crust accumulates the sedimentary burden that will one day be compressed into the metamorphic core of a range that does not yet exist even in geological imagination. The mathematics of plate motion operate with clockwork precision, each year bringing the opposing continental margins 2 or 3 centimeters closer to their ultimate embrace, a convergence rate so measured that entire species evolve and vanish in the time required for significant approach. Subduction zones consume oceanic lithosphere with methodical efficiency, their deep trenches marking the locations where ancient seafloor begins its journey into the mantle, carrying with it the accumulated sediments and volcanic debris that record millions of years of oceanic history. The descending slab releases water and other volatile compounds as it heats during its descent. These fluids rising into the overlying mantle wedge where they trigger partial melting and magma generation that will eventually feed the volcanic arcs that mark the early stages of mountain building. The chemistry of these arc magmas reflects the complex interplay between oceanic crust, accumulated sediments, and mantle material, their compositions preserving information about the geological history of the subducting plate and the thermal structure of the subduction system. Accretionary wedges build systematically at the leading edges of overriding plates, as oceanic sediments are scraped from the descending slab and incorporated into growing complexes of deformed and metamorphosed marine deposits. These chaotic assemblages of turbidites, oceanic basalts, and deep-sea sediments represent the early stages of continental growth, their complex structural relationships recording the progressive accretion of oceanic materials onto continental margins. The systematic addition of these exotic terrains creates the geological foundation upon which future mountain ranges will be constructed through continued convergence and collision. Thermal anomalies associated with subduction systems create regional metamorphic belts, where oceanic rocks experience systematic changes in mineral assemblage and texture as they are heated and compressed during their incorporation into continental margins. Blueschist and eclogite facies assemblages record the high-pressure, low-temperature conditions that characterize subduction zone metamorphism, while amphibolite and granulite facies rocks preserve evidence of the higher temperatures that develop in deeper parts of the accretionary system. These metamorphic gradients provide detailed information about the thermal structure and pressure-temperature evolution of ancient subduction systems. Magmatic arcs develop through the systematic emplacement of calc-alkaline intrusions that record the progressive evolution of subduction-related volcanism from initial oceanic arc development through mature continental arc magmatism. The compositional evolution of these igneous suites reflects systematic changes in crustal thickness, sediment input, and mantle source characteristics that occur as subduction systems mature and evolve toward eventual collision. Bathylitic complexes represent the plutonic roots of these volcanic systems, their crystallization ages and compositional variations preserving detailed records of magmatic processes that operated over tens of millions of years of subduction history. Continental collision begins when buoyant continental crust enters the subduction zone and resists further descent into the mantle, creating conditions where horizontal compression replaces vertical subduction and true mountain building begins through crustal thickening and structural telescoping. The transition from subduction to collision often occurs gradually over several million years as progressively more continental material becomes involved in the convergent system, creating complex temporal and spatial patterns of deformation that reflect the changing dynamics of the plate boundary system. The resulting mountain ranges preserve detailed records of this transition in their structural relationships and metamorphic histories. Foreland basins develop adjacent to rising mountain ranges as the lithosphere flexes under the load of thickening crust. These sedimentary deposenters receiving enormous volumes of erosional debris from the growing highlands, while simultaneously recording the subsidence history and flexural response of the continental margin. The stratigraphic sequences preserved in foreland basins provide detailed chronologies of mountain building episodes, their grain size variations and compositional changes reflecting the systematic evolution of topographic relief and erosional patterns in the adjacent highlands. These sedimentary archives often preserve the most complete available records of orogenic development and landscape evolution. Crustal melting accompanies the advanced stages of continental collision as thickened crust reaches temperatures sufficient to generate granitic magmas through anatexis of pre-existing crustal rocks. These leucogranite intrusions marking zones where metamorphic temperatures exceeded the solidus of common crustal compositions. The timing and distribution of crustal melting provides important constraints on the thermal evolution of collisional origins, while the compositional characteristics of anatectic melts preserve information about the crustal sources involved in magma generation. These high-grade metamorphic and magmatic processes create the deep infrastructure that will support surface topography during peak orogenic development. Strike-slip systems often develop within continental collision zones as oblique convergence and lateral escape tectonics accommodate convergent motion through complex combinations of compressional and transcurrent deformation. These fault systems creating linear zones of intense deformation that can extend for hundreds of kilometers across orogenic belts. The kinematics and timing of strike-slip motion provide important information about the stress field evolution and deformation mechanisms that operate during continental collision, while associated pull-apart basins and restraining bends create distinctive depositional and structural environments that preserve detailed records of transpressional and transtensional processes. What mystery governs the precise timing of mountain birth, determining when the slow convergence of continents will culminate in the dramatic emergence of new topographic relief that marks the transition from submarine geology to subaerial landscape processes? The answer lies in the complex feedback relationships between crustal thickening, surface uplift, and erosional efficiency that determine when growing mountain ranges achieve sufficient elevation to influence atmospheric circulation patterns and trigger the climatic feedbacks that will ultimately control their long-term evolution. Seismic tomography reveals the deep structure of active collision zones where descending slabs, thickened crust, and mantle flow patterns create three-dimensional velocity anomalies that extend hundreds of kilometers into the Earth's interior. These subsurface images providing insights into the deep, driving forces that power surface mountain building processes. The seismic structure beneath modern collision zones like the Himalayas and Alps provides natural laboratories for understanding the deep Earth processes that operated during ancient orogenic episodes. Their velocity patterns and attenuation characteristics revealing information about temperature, composition, and deformation mechanisms operating at depths inaccessible to direct observation. GPS measurements document the modern kinematics of active mountain building in collision zones, where convergent motion continues at rates of several centimeters per year. These geodetic observations providing real-time constraints on the deformation processes that shape growing mountain ranges. The systematic patterns of horizontal and vertical motion revealed by satellite positioning demonstrate the complex three-dimensional nature of mountain building, where surface uplift, lateral extrusion, and distributed deformation combine to accommodate ongoing convergence between continental plates. These observations enable calibration of mechanical models for mountain building processes and provide quantitative constraints on the rates and mechanisms of orogenic development. Climate modeling studies predict the atmospheric consequences of future mountain growth, as rising topography will create new barriers to atmospheric circulation that redirect precipitation patterns and modify regional climate systems in ways that will influence the erosional processes that ultimately determine mountain longevity. The feedback relationships between topographic growth and climate evolution represent one of the most complex aspects of mountain system development, where surface processes and deep earth dynamics interact through atmospheric intermediaries to create coupled systems whose behavior emerges from the interaction of geological and climatic forcing mechanisms. Analog. Modeling experiments using sand, clay, and other materials provide insights into the mechanical processes that control mountain building through scaled physical simulations of continental collision. These laboratory studies revealing the fundamental relationships between convergence rate, crustal strength, and deformation style that determine the structural architecture and topographic development of collision zones. The systematic variation of experimental parameters enables exploration of parameter space that extends far beyond the range accessible through natural examples, creating opportunities to understand the mechanical controls on mountain building processes under conditions not represented in the modern geological record. Only took plate tectonics this long to perfect the art of continental collision, learning through repeated experiments across geological time that the most dramatic mountain ranges emerge from the patient convergence of continents across ocean basins that require tens of millions of years to close. Only took subduction this long to discover that its greatest achievement lies not in consuming oceanic crust, but in preparing the geological stage for the collision episodes that will create the next generation of alpine landscapes. Only took the next mountain this long to begin its slow gathering of tectonic forces, accumulating the crustal materials and thermal energy that will eventually conspire to lift new peaks towards skies that do not yet know their names. And so the circle closes in the quiet arithmetic of deep time, where the mountain that began this narrative as a towering presence in the imagination has completed its patient transformation into the scattered elements that will birth the next range, its substance now distributed across ocean floors and continental margins in chemical signatures that await their geological resurrection. The summit that once caught starlight on crystalline faces exists now only in the mineral memories preserved within sedimentary layers, its elevation reduced to the gentle undulations of eroded roots that betray no hint of their former alpine glory. This transformation represents neither ending nor beginning, but simply another verse in the endless geological poem that Earth has been composing for 4 billion years. The feldspar crystals that once formed the mountain's granite heart have learned the patient art of becoming clay. Their silicon and aluminum atoms now arranged in layered structures that will eventually consolidate into shale formations where they will wait in darkness for the next cycle of compression and metamorphism to begin their slow conversion back toward igneous minerals. The calcium ions liberated from plagioclase dissolution have journeyed through groundwater systems toward ocean basins where they participate in the construction of limestone reefs that will one day be uplifted and folded into new mountain ranges by tectonic forces not yet imagined. Even the resistant quartz grains that survived multiple cycles of weathering and transport rest now in sandstone formations that preserve in their rounded textures the memory of wind and water that carried them across continental distances. Somewhere in the deep places where continents dream of collision, new magmas gather strength in chambers that exist 20 kilometers below surfaces that have never felt earthquake or erosion. These molten masses will cool with the same patience that characterized their ancient predecessors, crystallizing grain by grain into granite batholiths that will form the structural backbone of mountain ranges whose first stirrings may not reach the surface for another 50 million years. The cycle prepares itself for repetition with the quiet confidence of processes that have operated since the first continental crust achieved sufficient thickness to support significant topographic relief. The lessons learned by the vanished mountain echo through the geological principles that govern all such transformations, that permanence represents the greatest of all illusions, that the most enduring features of the landscape exist in constant flux through processes too slow for human perception, but too thorough for any form of genuine resistance. Stone learns to forget its crystalline ambitions one molecule at a time, while water writes new stories in the ancient language of chemical weathering. Frost discovers that patience accomplishes what violence cannot achieve, and wind demonstrates that the most effective erosion often proceeds through the gentlest means applied with geological persistence. The next mountain stirs in its tectonic sleep, gathering the materials and energy that will lift new peaks toward ancient stars that have watched this cycle repeat itself through countless iterations across the vast expanses of planetary time. In the end, mountains represent not monuments to permanence, but celebrations of change. Their brief, vertical gestures marking moments of dynamic equilibrium in a planet that breathes through the slow expansion and contraction of its solid surface. The mystery lies not in their eventual disappearance, but in their continual return. Each new range built from the recycled substance of its vanished predecessors in an endless spiral of geological resurrection that connects the deepest past to the most distant future through the patient arithmetic of stone becoming sky, becoming stone again.